Okay, so welcome back. Remember last time we ended with the definition of a function. And not just a function between, say, like the real line and the real line, but between any two arbitrary sets. Okay, so we had a function f from a to b between sets a and b is simply a subset of a cross b, so that if we have a, b is in f, and a, c is in f, implies that b is equal to c. Okay, so we think of an element in f as the point a, f of a. Right, so a is in a, and f of a is in b, and this tells you where the function sends the element a. And then we saw that you can also visualize this, so we can visualize f from a to b. Well, in certain cases, if a is nice, or b is nice, like the real line, then we can draw the graph of the function in the xy plane. This is something that we've all seen. In general, you just get something where, well, a will just look like a bunch of points, b will look like a bunch of points. This is just a general picture. I mean, it might, usually you might know more about your two sets. And then you draw arrows between the elements. Okay, so the arrows indicate where this function goes, or where each element in A gets sent under B. So I don't know, I'll send that one there, and that one will go there too. Okay, so from this we had, from a function, so from this function we get two kind of operations on sets. So namely, we can take a subset of A and map it to a subset of B under F, or we can also look at a subset in B and see what gets mapped into it. Okay, so I might have, I don't know, this might be my subset C of A, and these all got sent to this point f of c. Or I might look at, say, this is my D, and then, so D is a subset of B, and then I can look at the things that get mapped into D by F. So here it would be these 2 points, and then a notation here is F inverse of D. Okay, so let me just write these out. So if I have any subset of A, then f of c was the B in B, so that B is equal to f of c for some c in C. And if D is contained in, contained in B, then the inverse or the pre-image of D is exactly the A in A, so that f of A lies in D. Okay, so this is the image of C, and this is the pre-image of D. Okay, so in the picture that I wrote, there were 2 elements in D, and they both got sent to one element of the pre-image, so the pre-image was 2 points as well. You can also have pre-images that are strictly larger sizes, right? So if I took the pre-image of this set here of f of c, then I would get, I would start with 1 point and then I pick up 3 points, because all of these elements get sent to the same element of B. Okay, so that's something to notice, even though we use the notation F inverse of D, so the notation does not imply that that F has an inverse. F has an inverse, which would go from B to A. Okay, so what do I mean by an inverse function is just, it would be an element going from B to A, so that if I plugged in an element A, it would go to F of A, and then F inverse would send it exactly back. Okay, so we'll see that that some functions don't have inverses. So let me see a first example of this. Which is our favorite example, or one of them. So F goes from the real line to the real line, and it sends F of x to x squared. Okay, so I want to think about, or I want you to think about, is there an inverse for F? Okay, so I'll write pause here. Okay, so the answer turns out to be no. I'll just give one reason why. So notice that F of 1 is the same as F of negative 1, which is in particular 1. So then you can ask what F inverse of 1 has to be. Well, the fact that F of 1 is 1 tells you that F inverse of 1 should be 1, since 1 goes to 1, so therefore the inverse of 1 should go to 1. But it also should be, it should also be minus 1, since F of minus 1 is 1, and therefore minus 1 should get sent to 1, and then therefore the inverse should send it back to minus 1. But now we have two choices. I mean, we have that has to get sent to two different things, which means it's not a function. Okay? So F inverse, not a function. Okay, and let's see what in general happens here. Okay, so here's just kind of another thing exemplifying this behavior. If I take the image of 1, 2, okay, of the interval 1, 2, notice I get the closed interval 1, 4, okay. On the other hand, maybe you should just think about this. What do I get if I have the preimage of 1, 4? Well, I get 1, 2, right? That's everything in here gets sent into that interval. But I also get the interval negative 2 to negative 1. So that means that if I look at, so what I'm doing is I'm saying F inverse, so the preimage of the image, so this is the image of 1, 2, then I'm taking the preimage, is strictly larger than the thing that you started with. Okay, so you can take sets, you take an image, and then you take a preimage, and all of a sudden you get something larger than you would expect. Okay, so this will be kind of homework 2 is kind of an investigation into this. Okay, so another useful way to think of this is that F from A to B pushes information from the set A to the set B. Okay, so I don't know, A might be days of the week. B might consist of the set of breakfasts I eat. So, I don't know, cereal, oatmeal, yogurt. Okay, and the function of a day is the breakfast I ate on that day. Let's just say I'm a creature of habit. Every single day of the week, I eat the same exact breakfast. But I can change it up during the week. That's essentially true, actually. What is important here? So it's useful to know when the information is lost. So whether or not f is invertible. So what I mean here is that, well, if f is invertible, it would mean that I can recreate from the cereal or from the breakfast that I ate what day of the week it was, right? So the inverse function would be you feed in a breakfast and I spit out the day of the week that I consumed that breakfast. On the other hand, what if I have, so what can happen though, is I might take Monday, might be an oatmeal day, and Wednesday might be an oatmeal day as well, and now I've lost information. Right? Before I started with two distinct things. You know, there was the day Monday, the day Wednesday. I go over, now all I know is that I eat oatmeal. And I can't tell, if I know that I eat oatmeal, I can't tell whether it's Monday or Wednesday. Right? So, just from knowing I ate oatmeal, doesn't let me know what day it is. It could be any of those days. Know if it is Monday or Wednesday. Okay? So an invertible function would imply no loss of information. Because I can take any element here, say this is now just going to be my set A, it gets sent over in some way to the set B, but I know that if at every point there's a unique point that maps onto it and I can construct an inverse, then I can recreate from the element B exactly what the element A was. Okay, so if I had 7 different color shirts and I wore the same colored shirt on every day, then you would know if I was wearing a green shirt, you would know it was Monday. If I was wearing a blue shirt, you know it was Tuesday. Okay? That's not exactly true. I don't even know if I have 7 different colors of shirt, but in any case. So let me just give you a definition now. I've been kind of saying it over and over, but I'm making it formal. So we say f from A to B is injective, or 1-to-1, if for every pair of elements in A, so this is going to be my useful notation, which I don't think I've done before. So this is for all or for every. Okay, so it's an upside down A. The condition is if I have these, if f of A1 is equal to f of A2, this implies that A1 is equal to A2. Okay, another way to say this is just for every A1, A2 in A, if I start with distinct elements, so A1 is not equal to A2, this implies that f of A1 is not equal to f of A2. These are precisely the contrapositives of each other. Okay, so let me tell you now kind of a surprisingly powerful observation. Which I won't even formally prove yet. But so let's suppose A and B are finite. So A and B are finite sets. Okay, so we can just list their elements. And suppose that I give you the fact that there's a function from A to B which is injective. Okay? So then I want you to think about what can I say about the cardinality of A and the cardinality of B. Okay? I'm just going to pause here to think about that. Okay, so the conclusion that you can reach is that if f from A to B, so if f from A to B is injective, then the cardinality of A is strictly less than the cardinality of B. Okay? So maybe I'm just going to write down the contrapositive of this as well, and then give you a non-obvious application, just so you can see that this is kind of, when I say surprisingly powerful, I'm not just making stuff up. Okay, so the contrapositive is called the pigeonhole principle. And what it says is that if the cardinality of A is, so I messed up. I should have said if f from A to B is injective, the cardinality of A is less than or equal to the cardinality of B, right? They could have the same cardinality. That's fine. It just can't be greater. So the contrapositive of that, is if the cardinality of A is strictly greater than the cardinality of B, then there is no injective function from A to B. Okay, and so what this means is that if I have a function from A to B, then there exists, so there is A1, A2, and A, so that f of A1 is equal to f of A2. Okay, so this seems kind of completely obvious, right? If you have more things, then there's no way, and you map them over to less things, then at least two of the things are going to go to the same place. Okay, so let me give you a not so obvious application of this. I think this is probably, you can Google or go on Wikipedia for many more applications of this. Non-obvious. Okay, so suppose you are at a party, or suppose there is a party. Not very, well, I would like to say it's not very realistic in these times, but, who knows if that's the case. So suppose there is a party, it doesn't, well, I'll just say with n n people. Okay, so n can be n some natural number. Okay, you can think of 100 if you want. Okay, so then I claim there are two people there, actually at least two, who shake hands with the same number of people. Okay, so I guess this is, it's an old-fashioned party. You have n people around. They're all shaking hands with one another. In fact, notice that and what could happen is that no one shake hands with anybody. Well, then, everyone has shaken hands with 0 people. That's fine, okay, and this is still true. But once people start shaking hands, it's going to turn out that there will always be at least 2 people who shake hands with the same number. Okay? Oh, with the same number of people. Okay, so so why is this? Well, we're going to define a function. So first, let me tell you where the sets are. So we're going to define a function from A, which is the people in the party, or at the party, and the set B is just going to be the numbers 0 to n minus 1. Okay, so there's n people here, and the function, which goes from A to B, takes a person, and it goes to the number of people that person shakes hands with. Okay, so now, this is a set. So notice that both A and B have the same cardinality, right? Have cardinality n. On the other hand, and this is the little trick, so this is the usual thing with all of these pigeonhole principle problems. There's always one little trick, which again always kind of seems obvious, but leads you to some pretty surprising conclusions. Okay, so on the other hand, how do I say? So 0 and n minus 1 cannot both be in the image of f. Okay, so remember, so if 0 is in the image of f, so maybe 0 is f of a, this means that there's a person A has not shaken hands with anybody. If f of b is n minus 1, person B has shaken hands with everyone, or everyone else. So these are incompatible, right? You can't have one person who hasn't shaken anybody's hand and another person who has shaken everyone's hand. So therefore, the image of f has cardinality less than n. So we have the set A, which is n. The image of f is less than n. By the pigeonhole principle, this means there's 2 people A1 and A2, which have the same image, and therefore have shaken hands with the same number of people. Okay, so there's kind of every application is kind of like this. You get some sort of seemingly surprising coincidence, right? People that have shaken the exact same number of hands, and the reason is just that there's more input than there are possibilities. You can say the same thing that, there's going to be two people in the United States that have the same exact number of hairs on their head. Why? Well, there's 350 million people here, and I think we have much less number of hairs on our head than that. Anyways, so let me stop moving this around. So here's, let me give you another example, not of the pigeonhole principle, but what we really want to do, what we'll see a lot of in this class, is we want to extrapolate this fact that if f of a, that if f from A to B is injective, that the cardinality of A is less than the cardinality of B. What we really want to do is extrapolate this fact to infinite sets. And somehow I keep forgetting, so less than or equal to. I keep forgetting that. Okay, so let's see if we can make sense of this. All right, so here's the example. So is there a function which goes from the natural numbers to the real numbers, which is injective? Okay, so I'll pause here. You can think of it. Well, sure there is, right? There's, I can just take f of n to be n. I mean, there's actually tons of injective functions, right? These are all sequences that don't have the same value every time. So f of n equals n is a perfectly good injection. And we say then that the cardinality of n is less than or equal to the cardinality of R. Okay, so what can happen? So either the cardinality of n equals R, or the cardinality of n is strictly less than R, less than the cardinality of R. And if we're doing this extrapolation of saying this smaller cardinality is equivalent to an injective function, we're going to then ask the question, is there an injective function from going the other way, from the real numbers to the natural numbers? Okay? And so the answer is, well, let's wait. Okay, we're going to see this later in the class. This is kind of the, thinking about questions like this is really the start of a whole kind of beautiful branch of mathematics, which we'll see part of. Okay. So here's like another question in a kind of similar spirit. Okay. Is there an injection from the natural numbers to the Cartesian product of the natural numbers with itself? Okay, so in this case there is, right? Yes. And you just send, there's tons of different options, but you could send n to just n1. You can check that is injective. And I encourage you to do so just as a nice, easy exercise. Okay, so on the other hand, you can ask, what about is there something from the from the Cartesian product of the natural numbers to the natural numbers, which is injective? So again, the answer is going to be wait, but think about. Okay, so we're going to build some more kind of structure before trying to attempt these questions, but we'll get to them soon. Okay, and then when f is surjective and injective, we say f is bijective. And in that case, you really think of A and B as, in some sense, containing the exact same information. There's this just way to, well, I'll just draw a picture. You have A and B. There's a way to get every single element of B as some element of A, and in fact, there's a unique way to do that. Okay, so the picture is here. So a bijective F just kind of, in some sense, permutes the elements of A, or turns them into elements of B, but in a one-to-one way, and you don't miss anything of B. Okay, so here's an example. So F is going to go from the real numbers -2 to the real numbers -5. All right, and we're going to send x to 5x plus 1 over x minus 2. And now we want to show that f is so we're going to show that f is bijective. Okay, and I hope that this will give this gives the hints in general of how you want to show a function is injective and surjective. All right, so maybe I should just say that. Show f is bijective, so i.e. show f is injective. And surjective. Okay, so let's do injective first. So to check injective, you watch out for collisions. Right? You don't want to have two elements map onto the same element. So what do? You suppose that you have x1 and x2 in the domain, so that f of x1 and f of x2 are the same in the range. Oh, so maybe I should have said this a little while, just a second ago, but you should check that this is that the domain and range are correct. Okay, i.e. you can plug in any real number that's not 2, and you spit out a real number that's not 5. Okay, so now we're going to take two elements here. If they are the same, what we want to conclude is that x1 is equal to x2. Okay, so this just means that we're going to plug into the function f, x1 and x2, set them equal to each other, right? That's what we're assuming, they're equal, and we want to conclude that these values are equal. So you end up with 5x1 plus 1 over x1 minus 2 is equal to 5x2 plus 1 over x2 minus. And, well, what do you do now? You see fractions that are equal. The only thing that you're allowed to do at this point is cross multiply. x2 minus 2 is 5x2 plus 1 x1 minus 2. So you end up with, let's see, 5x1 x2 minus 10x1 plus x2 minus 2 is 5x1 x2 minus 10x2 plus x1 minus 2. Let's see what happens now. Ooh, I'll even switch my colors. So this cancels. This cancels. So this goes over. That goes over. So I'm left with 11x1 is equal to 11x2. So we're good. x1 has to be x2. Okay, so therefore it's injective. We said if two elements are equal, we assumed, this was our assumption. And this was our conclusion. So that's exactly what you want to show for an injective function. Okay, so what about surjective? So now we have a slightly different story. Now we're going to take, I'll call it y. So we're going to take y in our range, and we have to find an x in the domain so that f of x is equal to y. Well, so how do we do this? Well, now that you're just solving, the equation y is equal to 5x plus 1 over x minus 2, and you have to solve for x. All right, so this is, if you've seen computing an inverse of a real valued function, this is essentially what you're doing here, but now you're just looking for the specific value of y. Okay, so now what do you do? Maybe I'll just say, well, you do some algebra, which you can check, and you get that x has to be 1 plus 2y over y minus 5. And so now so now what do you have to say? Well, does this work? i.e., is this a real number? And the answer is, well, if y is a real number, this is a real number as long as y is not equal to 5. Okay, but we exactly showed that y is in the real, we assumed that y is in the real numbers minus 5, okay? And therefore, we just get this as our answer. So notice I could have said, so this proves that this function is bijective, so therefore f is bijective. But notice again, it's only, being a bijection strongly depends on what your domain and your range are, right? So I could have defined f going from the real numbers minus 2 to the real numbers, given by the exact same formula. Okay, so x goes to 5x plus 1 over x minus 2. And now this is no longer a bijection because 5 is not in the image. Right, and we saw that this is exactly, well, if I try to hit 5, I exactly have to divide by 0 here, which is not a real number. Okay, so this is essentially what you kind of always, the same setup works for all injective and surjective functions, so maybe I'll just write it. So if you want to show a function is injective, well, you take two values in the domain, plug them into f, and show that if they're equal, then you actually started with the same value. Okay? And surjective, well, you start with something in the range, and you just have to find, something which maps onto it. And somehow this is, you can, when you have an equation, right, this is very, you can do some algebra and solve these things. In general, there's no great, if I just give you a function between two sets, there's no great way to work out what an inverse is. You just have to, check, depending on the context. Okay, so that is all for today. Thanks.